This video will talk about the mole. So the mole, and the funny thing is it's actually Mole Day today as I record this video, so that's exciting. You can ask me about Mole Day when you come to class. What is the mole? So the units are MOLE, or MOL for short. Now, all it is a counting number, and it's very much an overcomplicated topic. So my goal in this video is to just simplify it and make sure you understand it and have an idea of what it actually is. Because the more you can understand what the mole is, the easier it will be to do problems with the mole. And when I learned about the mole the first time, I remember I figured out how to do the problems, but I didn't really understand what the mole was. So my goal is to make sure you really understand the background of it. So my first question is, what is a dozen? What comes to mind when I say a dozen? And my guess is that you think of the number 12. And you probably start thinking of things like 12 donuts, 12 eggs, things that we count in a dozen, things that are counted by the dozen. Now, the same thing happens to a chemist. When you say the word mole, I think of this number. Instead of 12, I think of this number. Now, the only difference between the mole and a dozen is that this mole is this number is huge, where a dozen is just 12. 12 is a manageable number. The thing that makes this overcomplicated for some reason is that we're just using a massive number. And the reason we use such a large number like this is because we're counting atoms, and atoms are incredibly small. So to have a decent number of them, or a visible number of them, we have to have a large number of them. And it so happens that this tends to be a pretty nice number to work with. And I'll explain why this number is a nice number to work with. So again, when we count atoms, we count them by the mole. So you see we might say 1 molecule of N2, or we might count them by the mole instead. 3 moles of hydrogen react to form 2 moles of NH3 ammonia. And here's a sample of 1 mole of 8 different elements. So you can see there's 1 mole of each. Now the masses are different. If you look, the masses of each mole are different. But what all of these samples have in common is there's this many atoms of each element in each of these samples. So there's this many atoms of zinc, this many atoms of copper, this many atoms of magnesium. For each of these samples, they may have different masses, different volumes, take up more space, but they all have the same number of atoms there. It's kind of like if I go back to the eggs and the donuts that I just showed you in the previous slide. 12 eggs and 12 donuts take up a different amount of space. They have different masses, but there's 12 of each. That's what they have in common, the number of them. So this slide right here I think is an important one. We've got Avogadro's number. That's what we call this number, and I'll talk about that next slide. Avogadro's number is 6.02 times 10 to the 23rd. That's why this is Mole Day today. I'm recording this on October 23rd, 1023. Now a single molecule. We've got 1 molecule of H2O. So this is H2O. 1 molecule, if you add it up on the periodic table, hydrogen weighs about 1 AMU and oxygen weighs about 16 AMU. Now, because there's 2 hydrogens, I got to multiply this by 2, so this equals 2 plus 16. That's where I get the 18 AMU. So 1 single molecule weighs 18 AMU. But I'm going to tell you, you're probably never going to work with a single molecule of water ever in your chemistry class because it's really, really small. Anytime you pour even a single drop of water out of the sink, you're working with trillions and trillions of water molecules. So the AMU units here aren't that useful because we just never really use that small of masses in chemistry. So what chemists did is they said, okay, let's weigh out 18 grams of water. So it's the same number, just instead of AMU, let's weigh it out in grams. And then they asked how many molecules of water are in this 18 gram sample. They found out that it's this number. That's where the number comes from. And I have a whole nother slide where I'm going to break this down even more. But that's an intro. And you're going to see I'm going to repeat these things just so you really understand what the mole is. Okay, Avogadro's number. So here's just a few quick notes. I'll let you write them down. And then we'll move on. So the Avogadro's number is the number of particles in 1 mole. So 1 mole equals 6.02 times 10 to the 23rd. And now it could be anything. It doesn't have to be atoms, molecules, or things like that. You could say I want 1 mole of donuts. It's just that doesn't exist, right? There's no such thing as 6.02 times 10 to the 23rd donuts. No bakery can handle that capacity. So it's a huge, huge number that we don't really use it to count anything else just because it's too big. But when it comes to atoms, it's really useful to have a large number like that. So it's useful for counting atoms, formula units, and molecules. Again, here's the number. So we say 6.022 times 10 to the 23rd particles per mole. And whenever I say particles, that could mean atoms, formula units, which we abbreviate FUs, and molecules. And you can see this is a really, really big number. In class, I'll give you some examples of just how large this number is if you use it to talk about ordinary things. But what it allows us to do is it allows us to convert from moles to atoms, molecules, formula units. And it does come in handy for a lot of things. It's very much the central unit of chemistry. You don't go very far in chemistry class without using the mole. Especially as you move higher and higher. You take college chem, the first thing you're going to be doing is using the moles pretty regularly. So once we learn about it, you'll see that we'll use it quite a bit. Now when we talk about formula units, atoms, and molecules, obviously an atom, we know what that is. That's an individual particle of an element. So an atom is a single particle of an element, so that would be like a single copper atom. Now when elements combine, they form compounds. Now they can either form, if you remember, covalent compounds or ionic compounds. So we use the word molecule to talk about a covalent compound. And then formula unit is used for ionic compounds. So you don't need to know a lot of that right now. We'll get back to that later in the year, and you'll get that down better. So we'll just move on for now. Okay. Now, why 6.022 times 10 to the 23rd? Where does this number come from? This is, I spent a little bit of time on this on that slide with the water, but I'm going to really hit it hard on this slide. So we're going to take two different elements, carbon and oxygen. Let's say we have a single atom of each. I have one atom of carbon, one atom of oxygen. And if you look on the periodic table, this number here tells us that one carbon atom weighs 12.011 AMU. So we got AMU in here, and you can see I went a little overboard on my animations on this slide. And then the oxygen atom weighs 15.99 AMU. But again, I told you already that we don't really ever work with a single atom of anything. So what we're going to do, and here's the reason why. This is how many grams a single atom of carbon weighs. So this is the mass of a single carbon atom. We got the mass of a single oxygen atom. And again, it's so small that it's not useful for the most part. Unless you're doing really, really advanced chemistry, it's not, in very specialized experiments. Most chemists never really use single atoms. So what we're going to do instead, we're going to take a sample of carbon that weighs the exact same value but in grams. So same number, different units. So we're moving from AMUs to grams. And we're going to do the same thing with oxygen. We're going to take the same number, so this number that's on the periodic table over here, we're going to take that same value but in terms of grams. And now if I ask how many carbon atoms are in this chunk of carbon over here, so how many carbon atoms are in this sample, and then if I ask how many oxygen atoms are in this sample, notice they have different masses, but what they both have in common is that they have the same number of atoms. They both have 6.022 times 10 to the 23rd atoms. So this is the number that basically allows us to take our numbers in AMU. So I'll actually go back. It allows us to take this number here. Instead of using it as AMUs, we can now use it in terms of grams. And we actually say grams per mole. This is how many grams per mole, the mass of carbon per mole, I should say. That's where the 6.022 times 10 to the 23rd number comes in. If I count how many atoms are in this sample, I count how many atoms are in this sample, it is the same number. Okay, why are moles useful? Again, I already told you that they're kind of the central unit of chemistry. They allow us to convert between many different properties, many different things. It allows us to go from moles to concentration, to number of atoms. We use them in gas laws in a little bit, or that's actually towards the end of the year in second trimester. Allows us to go from mass to moles. And it allows us to work with balanced reactions and count atoms and keep track of them. Super, super useful. So I'll let you write this down and then we'll move on. You might have to pause. Okay, the last slide here that I'm going to cover for this video is how many molecules are in 8.5 moles of CO2. So this isn't in your notes, you don't need to write anything down. But if I were to ask you how many donuts are in 8.5 dozen, or if I have 8.5 dozen donuts, how many donuts is that? And you would just say, okay, well, 8.5 times 12, right? And then you get your answer. What would that be? That's actually 100, isn't it? If I'm doing my math right in my head. So you could convert from 8.5 dozen to number of donuts. That wouldn't be a problem. Now, if we're doing this with chemistry, if I want to convert from 8.5 moles of CO2 to molecules of CO2, I'd set up a ladder, bring moles down, and you probably already figure out that you're just going to multiply by Avogadro's number, but molecules of CO2, moles of CO2, we'll extend that. Now, 1 mole of anything has how many things in it? And the answer is 1 mole of anything has 6.02 times 10 to the 23rd molecules of CO2. So my moles of CO2 would cancel. Then I'd take 8.5, which I'll do on my calculator here. 8.5 times 6.02, second E23. And what I end up getting to 2 sig figs is 5.1 times 10 to the 24 molecules of CO2. So what I just did here is I said, okay, I have 8.5 moles of CO2. How many particles or how many molecules of CO2 are in this 8.5 moles? Well, I multiply it by Avogadro's number because that's how many are in 1 mole. So if 1 mole is equal to this many, I just multiply it by 8.5, multiply them together here, and it tells me that there's this many particles if I have 8.5 moles. So that's an introduction to moles. We'll do a lab on the size of the mole. I'll talk about it more in class. There's not actually anything you need to do with these notes. We'll show you how to do some conversions in a future video. I'll show you how to do molar mass and things like that. So my goal with this video is to make sure you understand what a mole is. A mole is just a counting number, and it's used to count atoms and molecules and particles. So if you missed anything, maybe go back, watch some of those previous slides, and bring questions to class, because I know this can be a little tricky at first, but the more you understand the mole now, the easier chemistry will be as you move forward.